Hey everyone, Morgan here. So this is an updated version of the video answer key for the bond energy problems. Fixed a couple little math boo-boos, nothing too serious, but I did want to re-record this so that it would be a little more accurate. So AP Chemistry, bond energy problems. All right, so I'm going to basically bring these up on the screen for you one at a time. Okay, water, our goal is to go H2O gas to 2H gas plus O gas, which we call delta H naught kaboom. That's my own term, not an AP term or anything like that. We're just blowing up the whole molecule. So I look up the heat of formation for water, and remember that has to be as a gas, not as a liquid. So delta H naught formation is negative 241.8 kilojoules. I look up the heat of formation for hydrogen gas and for oxygen gas, boom, boom. I've already used those in the lecture before. So I rearrange the equations, H2O gas to H2 and 1/2 O2 gas, change the sign on the heat of formation because I've reversed it, multiply the heat of formation for hydrogen by 2, multiply the value by 2, take the oxygen as is. When I add the whole thing up, I get 926.68 kilojoules. Divide that by 2 because I'm breaking 2 bonds. And I get about 463 kilojoules. And that's a number that we're going to be using a little later on in the homework. Okay. Second one involves ammonia. Same basic ideas. Okay. I had a boo-boo on this page earlier. I had a 2 there that didn't belong there. Heats of formation are the formation of 1 mole of the substance. Okay, so I looked up the value for N gas, put it in, still using the one for hydrogen gas. Go through, do the work down here. Pause if necessary. This time I'm dividing by 3 because there are 3 identical bonds between nitrogen and hydrogen here. Get about 391. Now remember, if you're using a different set of data tables than I am, you can have little differences in these numbers. Don't worry about them so much. All right. Next one is the carbon to chlorine bond in carbon tetrachloride, 4 identical bonds. Goal equation, my heats of formation. This is one that it really depends upon what book you're looking at. I learned 17.38 kilojoules when I was in college. That came from the book by Dickerson, Gray, and Haight. Okay, some of the tables now are saying 715. Let's not lose any sleep over that. Pause if you need to look at those equations. Then we do the work down here. And I end up dividing by 4 because they're 4 identical bonds. And if you rounded that up to a whole number, that's great. Let's not worry about that so much. All right. So the rest of them, all very similar. I'm giving you structures here. Okay. We look up the carbon disulfide. Now, I've always treated sulfur in the natural state as rhombic sulfur. So that's why I chose S rhombic, 2 S rhombics. There is actually an S2 that's in the data tables. It's a pretty rare molecule though. So if you use that one, you're going to get a slightly different number over here, but don't lose any sleep because I'll look at your method and I'll see what's going on. And I'll know you've done it correctly just with a different value. Okay? And then down here, I ended up dividing by 2 because there were 2 identical double bonds. And again, always just pause these if necessary so you can read them off the screen. Okay. Carbon-oxygen double bond and CO2. Okay. Very familiar equations that we're working with. Very familiar setup. And then dividing by 2. All right. I'm doing a carbon to oxygen again in a different molecule, and there's a reason for this, which we'll get to in question 10, I think it is. So COCl2 gas, heat of formation, known equations. Then down here, I work it out. Now, here's where I have to do something a little bit different than the previous 5 problems. When I've got the structure, I've got 2 carbon to chlorine bonds and the carbon to oxygen bond. So when I get down here, I subtract the value for the 2 carbon to chlorine bonds that I got as my answer in problem number 3. That's where that came from. And I got 780 this time. Okay. HCN. There's the structure. I'm not expecting you to come up with structures at this point, don't worry. My goal equation, Givens, heats of formation. Now, when I got my delta H naught kaboom here, I subtracted 416 kilojoules. And that is something that I calculated in the lecture outline. That's where I got that value from. If you got a slightly different value out of the book, don't lose any sleep. Okay, number 8. Slightly more, oh, there we go, better. Slightly more complicated molecule. All those equations you already know. And over here. So, delta H naught kaboom, I one times 463. Here are the 3 bonds that are the 3 times 416, and then the oxygen to hydrogen that's over there, and I actually got that number from question or problem number 1 on this homework. Okay. Over here, number 9, there's the compound, a little more complex, a lot of bonds. I looked up the heat of formation. Did the same typical work. Now, I have to subtract a carbon-carbon bond. I got that out of the lecture outline. 3 times the carbon to hydrogen bonds for this carbon, and 1 carbon to hydrogen bond for the other carbon. So that's what these are. And I end up there. Okay. Now, a little comparison for a carbon to oxygen double bond. In CO2, I got 805. In COCl2, 780. And in that aldehyde for number 9, 726.5. So the bonds are not always going to be exactly the same energy in different molecules. It depends upon what else is there. Now we're going to talk about resonance in an upcoming chapter. That gives some stabilization to the structures, and it accounts for the differences in these bond energies. Okay? The molecules weren't all identical to each other, so the values can be a little bit off. Now, the fact is it's less than a 10% difference across all 3 molecules, so I'm really not terribly concerned about that. Okay, that is the bond energy homework. Thanks for tuning in. This is Morgan signing off.